In the autumn of 1940, as German bombers rained destruction upon British cities and the mechanized armies of the Third Reich dominated continental Europe with seemingly unstoppable force, Britain faced an industrial crisis that threatened to undermine its entire war effort. The crisis was not merely one of production capacity or raw material shortages, though these challenges existed in abundance. Rather, it was a fundamental problem of industrial philosophy, a deeply rooted conceptual limitation that prevented British factories from producing the armoured vehicles desperately needed to counter the German panzer divisions that had swept through France with such devastating efficiency. The British approach to tank manufacturing in the early years of the Second World War remained rooted in craft, traditions that would have been familiar to Victorian engineers. Each tank was essentially a bespoke creation, assembled by skilled craftsmen who fitted and adjusted components individually, filing metal here, shimming there, making countless small modifications to ensure that parts designed on paper would actually fit together in steel. A single tank might take weeks to complete, moving through various workshops where specialized teams worked on hull assembly, turret construction, engine installation, and final fitting. The process resembled shipbuilding more than modern manufacturing, with each vehicle representing a unique combination of hand-fitted components and artisanal adjustment. This approach had deep roots in British industrial culture. The nation that had pioneered the Industrial Revolution retained a profound respect for skilled craftsmanship, for the knowledge that resided in the hands and minds of experienced workers who could look at a problematic assembly and know instinctively how to make it work. These were men who had served long apprenticeships, who understood materials through years of direct experience, who could read blueprints but who also knew when to deviate from them to achieve practical results. Their expertise was genuine and valuable, honed through decades of building locomotives, ships, heavy machinery, and all the complex mechanical systems that had made Britain an industrial power. But expertise, however genuine, could not overcome fundamental limitations of method. While British craftsmen carefully fitted together tanks one at a time, German factories were producing armoured vehicles in quantities that reflected a different industrial philosophy entirely. And across the Atlantic, American automobile plants were beginning to demonstrate production capabilities that would soon dwarf anything Europe had achieved. The Americans had learned something that British industry had not yet fully grasped, that the key to mass production was not simply making things faster, but making them differently, with a level of precision and standardization that eliminated the need for skilled adjustment during assembly. Into this crisis stepped a man whose background seemed, at first glance, entirely unsuited to revolutionizing tank production. John Weeks was not a military engineer, not a tank designer, not even primarily a manufacturing specialist. He was an automotive designer and engineer who had spent his career working on passenger cars, light commercial vehicles, and the mundane but essential machinery of civilian transportation. His experience lay in an industry that had already undergone the revolution that tank manufacturing desperately needed, an industry that had learned through hard experience how to transform complex mechanical assemblies from craft products into mass-produced commodities. Weeks understood something that the traditional armaments industry had not yet internalized, that the automobile industry's achievement was not merely about assembly line speed or division of labor. Though these were important, the real breakthrough had been the development of what engineers called interchangeability, the principle that any component of a given type could fit into any vehicle without modification. This seemingly simple concept required a complete reconceptualization of how products were designed and manufactured, demanding levels of precision that traditional craft manufacturing had never needed to achieve. In traditional craft manufacturing, tolerances could be relatively loose because skilled workers would adjust components during assembly. If a shaft was slightly too large for a bearing, a craftsman would machine it down. If a plate didn't quite align with its mounting points, he would drill new holes or bend the metal slightly. If gears didn't mesh properly, he would lap them together until they did. This flexibility was actually seen as a virtue, as evidence of skilled adaptation to real-world conditions. But it meant that no two tanks were quite identical, that components from one vehicle couldn't simply be swapped into another. And that assembly required the constant attention of expensive skilled labor. The automotive industry had learned, through decades of development, beginning with the pioneering work of engineers like Henry Leland and culminating in the vast production systems of companies like Ford, that true mass production required eliminating all this adjustment. Every component had to be made to such precise specifications that it would fit correctly the first time, every time, with no modification needed. This demanded not just tighter tolerances, but completely different approaches to design, tooling, inspection, and quality control. It required thinking about manufacturing from the very beginning of the design process, rather than treating it as a separate problem to be solved after the designers had finished their work. When Weeks examined British tank production in detail, he found a system that violated virtually every principle of modern manufacturing. Blueprints specified tolerances that were achievable only through skilled hand-fitting. Components were designed without adequate consideration of how they would actually be manufactured at scale. Assemblies required access from multiple angles, making sequential assembly line production impossible. Different parts of the tank were built in separate workshops, then brought together for final assembly where inevitable misalignments would be discovered and painstakingly corrected. The entire process assumed the presence of highly skilled workers at every stage, workers who were already in desperately short supply and who could not be quickly trained or replaced. Weeks proposed something radical, redesigning British tanks from the ground up using automotive manufacturing principles. This was not merely a matter of making minor adjustments to existing designs. It meant fundamentally rethinking how tanks were conceived, how they were engineered, and how they were produced. It meant challenging assumptions that military engineers had held for decades, questioning practices that seemed self-evidently correct to men who had been building armored vehicles since the First World War. It meant, in essence, asking the British armaments industry to learn from an industry it had traditionally viewed as less sophisticated, less demanding, less serious than the grave business of manufacturing weapons of war. The resistance was immediate and substantial. Military engineers argued that tanks were not cars, that the demands of armored warfare required levels of strength, durability, and performance that could not be achieved through mass production methods. They pointed out correctly that tanks operated under conditions vastly more severe than civilian vehicles, that they had to withstand the shock of firing large guns, the stress of cross-country movement over brutal terrain, the impact of enemy projectiles. They argued that the craft approach, whatever its limitations in speed, produced superior vehicles whose quality could not be matched by assembly line methods. These objections were not entirely without merit. Tanks did indeed face demands that passenger cars never encountered, but Weeks understood that the objections confused different issues, conflating design requirements with manufacturing methods. The automotive industry had proven that products could be both precisely engineered and mass-produced, that tight tolerances and standardization actually improved rather than compromised quality. The question was not whether tanks needed to be rugged and reliable. Everyone agreed they did, but whether craft manufacturing methods were actually the best way to achieve that ruggedness and reliability. Weeks began his transformation with a detailed analysis of existing tank designs, examining every component, every assembly, every step of the manufacturing process. He brought to this task the analytical rigor of an automotive engineer trained to think systematically about manufacturing efficiency. Where military engineers saw a complex but essentially sound design that simply needed to be built, Weeks saw hundreds of opportunities for improvement, hundreds of places where the design made manufacturing unnecessarily difficult, where tolerances were either too loose or unnecessarily tight, where assemblies required skilled adjustment that could be eliminated through better design. Consider something as seemingly simple as a hull plate. In traditional tank manufacturing, these plates were cut from steel sheet, then drilled for mounting holes, then fitted to the hull structure. Because tolerances were loose, the actual position of holes often had to be adjusted during assembly to match the as-built rather than as-designed structure. This required skilled workers to measure, mark, and drill additional holes or elongate existing ones, a process that consumed time and introduced variability. Weeks redesigned the entire assembly to use precisely machined mounting points, jigs that ensured holes were drilled in exactly the right positions every time, and assembly sequences that guaranteed components would align correctly without adjustment. The result looked similar to the original design, but its manufacturing characteristics were completely different. This same analytical approach was applied to every aspect of tank design. Turret rings, those critical rotating interfaces that allowed the main gun to traverse, were traditionally hand-fitted to achieve the necessary combination of smooth rotation and weather-tight seal. Weeks redesigned them using principles borrowed from automotive bearing design, with precisely machined surfaces and standardized seals that could be assembled without fitting. Suspension systems, traditionally comprising numerous individually adjusted components, were redesigned as modular assemblies that could be built and tested separately, then installed as complete units. Engine compartments were reconfigured to allow engines to be installed from a single direction, using standardized mounting points, rather than requiring access from multiple angles with individually fitted brackets. The transmission represented a particularly challenging redesign problem. Military transmissions of the era were complex mechanisms containing hundreds of precisely machined gears, shafts, bearings, and synchronizers. Traditional manufacturing treated each transmission as essentially unique, with components selected and fitted to achieve proper gear mesh and bearing preload. This process required highly skilled machinists and assemblers who understood the subtleties of gear tooth contact patterns and bearing clearances. Weeks approached the transmission as a modular assembly of standardized subcomponents, each manufactured to tolerances tight enough that they could be assembled in any combination while still achieving proper function. This required significantly more precise machining, but it eliminated the skilled assembly work and created a transmission that could be built by less experienced workers, following clear procedures. But redesigning components was only part of the challenge. Weeks also had to rethink the entire factory layout and workflow. Traditional tank factories were organized by process, with separate areas for welding, machining, assembly, and finishing. Components moved back and forth between these areas as different operations were performed, accumulating transportation time and waiting time between productive operations. Weeks introduced the concept of flow production, organizing work so that components moved steadily through sequential operations without backtracking or waiting. This required careful synchronization of different processes, ensuring that each operation produced exactly what the next operation needed, exactly when it needed it. The implementation of this vision required massive changes to existing factories. Machine tools had to be relocated and in many cases replaced with more precise equipment. New jigs and fixtures had to be designed and built to hold components in exact positions during machining and assembly. Inspection procedures had to be completely revised, moving from subjective assessment by skilled workers to objective measurement using precision instruments. Workers had to be retrained, learning not just new procedures, but new ways of thinking about quality and precision. Supervisors and managers had to embrace new methods of planning and control, tracking production flow rather than simply monitoring individual operations. The transformation did not happen overnight, and it did not happen smoothly. Initial attempts to implement automotive manufacturing principles often failed, as workers and managers struggled with unfamiliar methods and equipment. Components that should have been interchangeable sometimes weren't, revealing problems with tooling or procedures that had to be painstakingly diagnosed and corrected. Assembly lines that should have flowed smoothly instead stuttered and stopped as bottlenecks emerged and unexpected problems arose. There were moments when it appeared that the skeptics had been right, that tank manufacturing truly was different, that automotive methods simply could not be adapted to armored vehicle production. But Weeks persisted, applying systematic problem-solving methods to each difficulty as it arose. When components didn't fit despite being made to specification, he analyzed the entire production process to find where variability was being introduced. When assembly operations took longer than planned, he redesigned them, breaking complex tasks into simpler steps that could be performed more reliably. When quality problems emerged, he strengthened inspection procedures and improved worker training. Gradually, through hundreds of incremental improvements, the new system began to work. Production rates began to climb, first slowly, then more rapidly, as workers and managers gained experience with the new methods. The results, when they finally emerged, were remarkable by any standard. Factories that had previously produced perhaps a dozen tanks per month began producing dozens per week. Manufacturing costs per tank fell dramatically as labor hours per vehicle declined and material utilization improved. Quality improved rather than declined, as precise manufacturing methods produced more consistent results than craft fitting. Most importantly for the war effort, the new system could be operated by workers with far less training than traditional methods required, allowing rapid expansion of production as new workers were recruited and trained. The impact extended beyond simple production numbers. Standardization and interchangeability meant that spare parts could be produced in advance and stored, rather than having to be custom fitted to particular vehicles. Field maintenance became simpler and faster as mechanics could replace entire assemblies rather than having to adjust and fit individual components. Training of tank crews became more efficient as vehicles became more consistent in their characteristics and behavior. The entire system of armored vehicle production, maintenance, and operation became more efficient as a result of applying automotive manufacturing principles. Other designers and factories took notice. The methods Weeks pioneered spread through the British armaments industry, adapted and applied to other types of military equipment. American manufacturers, already familiar with automotive production methods, were able to rapidly implement similar approaches when they began producing tanks for the Allied war effort. The Soviet Union, receiving technical assistance from American and British engineers, incorporated these methods into its own massive tank production program. By the middle of the war, virtually all major tank producers were using some version of the manufacturing philosophy that Weeks had introduced to British industry. The transformation represented more than just a technical achievement. It demonstrated the value of cross-industry learning, of applying insights from one domain to solve problems in another. The automotive industry and the armaments industry had traditionally seen themselves as fundamentally different, serving different purposes with different requirements and different standards. Weeks showed that the underlying principles of modern manufacturing transcended these superficial differences, that precision, standardization, and systematic process control were universally applicable concepts rather than industry-specific techniques. The story also illustrated the often overlooked importance of manufacturing in warfare. Military historians have traditionally focused on strategy, tactics, and battlefield leadership, treating industrial production as merely a supporting factor. But the ability to produce weapons in sufficient quantity and quality is often as important as the ability to employ them effectively. Germany's early successes in the Second World War owed much to superior manufacturing that allowed rapid replacement of losses and continuous upgrading of equipment. Germany's eventual defeat owed equally much to the Allied ability to outproduce Axis factories by enormous margins, a capability that rested fundamentally on superior manufacturing methods. Weeks himself remained largely unknown outside industrial circles, overshadowed by more famous generals, admirals, and political leaders. His contribution did not involve dramatic battlefield victories or stirring speeches. He never commanded troops or made strategic decisions that determined the outcome of campaigns. Yet his work arguably saved more lives and contributed more to Allied victory than many more celebrated figures, by ensuring that British and Allied forces had the equipment they needed when they needed it. His story reminds us that war is not only about combat, but about all the systems of production, logistics, and organization that make combat possible. The principles Weeks applied have only become more relevant in the decades since the Second World War. Modern manufacturing, whether of civilian or military products, universally embraces the concepts of precision, standardization, and systematic process control that were revolutionary in 1940. The automotive industry continues to be a leader in manufacturing innovation, developing new techniques that gradually spread to other industries. The defense industry, while still facing unique requirements, has fully embraced modern manufacturing methods, recognizing that craft production cannot meet the demands of contemporary military systems. There is a broader lesson here about innovation and institutional change. The British armaments industry of 1940 was not staffed by incompetent or unintelligent people. The engineers and managers who initially resisted Weeks' ideas were experienced professionals who understood tank design and production as it had been practiced for decades. Their resistance was not irrational, but rather reflected the difficulty of changing established practices, of questioning assumptions that seem self-evident, of learning from industries and individuals outside one's traditional domain of expertise. Real innovation often requires this kind of boundary crossing, this willingness to look beyond familiar methods and consider radically different approaches. The transformation also demonstrated the importance of systems thinking in addressing complex challenges. Weeks did not simply speed up existing processes or exhort workers to greater effort. He recognized that the problems with British tank production were systemic, rooted in fundamental design and manufacturing philosophies rather than in any particular step or procedure. Addressing these problems required changing the entire system, from initial design through component production to final assembly. Partial solutions would not have worked. Only comprehensive transformation could achieve the necessary improvements in speed, cost, and quality. Consider the challenge of training in this new system. Under craft manufacturing, becoming a skilled tank builder required years of apprenticeship, learning through observation and practice under experienced craftsmen. This approach worked well for maintaining traditional skills, but could not rapidly scale to meet wartime production demands. WWII's system broke complex operations into simpler steps that could be taught quickly through clear procedures and systematic practice. A worker who would have needed years to become proficient under the old system could become productive in weeks under the new one. This was not because the new system somehow made tank building simple, but because it reorganized the work to separate tasks requiring extensive experience from those that could be performed following standardized procedures. The evolution of inspection practices illustrates another crucial aspect of the transformation. Traditional craft manufacturing relied heavily on the judgment of experienced workers who could assess quality by eye and feel, determining whether components met requirements through methods that were difficult to articulate or teach. WWII introduced systematic inspection using precision measuring instruments, with clearly defined specifications and go-no-go criteria that could be applied consistently by different inspectors. This objectivity had multiple benefits. It ensured consistent quality standards across different workers and shifts. It provided immediate feedback when processes drifted out of specification, and it created records that could be analyzed to identify systematic problems requiring correction. The story of tank production transformation also reveals something important about technological change more broadly. We often imagine innovation as the work of lone geniuses having sudden insights, creating entirely new technologies through flashes of inspiration. The reality is usually more complex and more interesting. WWII did not invent any fundamentally new manufacturing techniques. The principles he applied, precision machining, interchangeable parts, flow production, systematic quality control, were already well established in the automotive industry. His achievement was not invention, but rather creative adaptation, recognizing that methods developed for one purpose could be applied to another, and working out the countless details necessary to make that application successful. This kind of innovation, transferring and adapting existing knowledge rather than creating entirely new knowledge, is perhaps more important in practice than breakthrough invention, yet it receives far less attention and recognition. Every industry, every organization, every field of practice has knowledge and methods that could potentially benefit others, if only the connections could be made and the details of adaptation worked out. WWII made such a connection, and in doing so helped determine the outcome of the greatest conflict in human history. The physical transformation of tank factories during this period was dramatic to witness. A visitor to a British tank factory in 1939 would have seen what appeared to be organized chaos. Tanks in various stages of completion scattered throughout large workshops, workers moving between them with tools and components. The whole scene, resembling a busy shipyard or locomotive, works more than what we would recognize as a modern factory. The same visitor returning in 1942 would have found a completely different scene. Tanks moving steadily along assembly lines, workers at fixed stations performing specific operations, components arriving exactly when needed from feeding production lines. The entire operation flowing with a rhythm and precision that would have seemed impossible just a few years earlier. This physical transformation reflected deeper changes in how work was organized and understood. Under craft manufacturing, the primary organizational unit was the skilled worker or small team, working relatively independently to complete complex tasks. Under flow production, the primary organizational unit became the process, with individual workers contributing specific operations within a carefully orchestrated sequence. This shift required workers to think differently about their role and contribution. Rather than taking pride in their ability to solve unique problems through skill and experience, they had to take pride in their ability to execute standardized procedures consistently and efficiently. This was not a simple change, and it met resistance from workers who valued the autonomy and creativity of craft work. Yet the new system also offered significant benefits to workers. Craft manufacturing required long apprenticeships and created sharp distinctions between skilled and unskilled workers. Flow production with standardized procedures allowed more rapid skill development and created clearer paths for advancement based on demonstrated competence rather than years of service. The new system also tended to be less physically demanding. as proper organization of work could eliminate many of the awkward positions and heavy lifting that craft methods often required. And perhaps most importantly, in wartime Britain, the new system created far more jobs, allowing many more workers to contribute meaningfully to the war effort. The management challenge in implementing this transformation was substantial. Factory managers accustomed to overseeing craft production had to learn entirely new methods of planning, scheduling, and control. Traditional management of craft production involved assigning jobs to skilled workers or teams and monitoring their progress, intervening when problems arose or when particular expertise was needed. Management of flow production required detailed advance planning to ensure that all necessary components and materials would be available when needed, careful balancing of different operations to maintain smooth flow, and systematic monitoring of quality and productivity metrics. Many managers struggled with this transition, and successful implementation often required bringing in experienced managers from the automotive industry who understood flow production methods. The broader economic implications of this transformation extended well beyond tank production. Britain emerged from the war with an industrial base that had been fundamentally modernized through the necessity of war production. The manufacturing methods pioneered in tank factories were applicable to many civilian products, and many factories that had produced tanks during the war converted to civilian production using the same basic methods. Workers trained in precision manufacturing during the war carried those skills into civilian employment. Managers who had learned flow production methods applied them to peacetime manufacturing. In this indirect way, the demands of war drove industrial modernization that shaped Britain's post-war economy. The contrast with Germany is instructive and somewhat ironic. German industry in the 1930s had pioneered many aspects of modern manufacturing, and German automotive companies were among the most advanced in the world. Yet German tank production during the war never fully embraced the kind of flow production methods that WWII introduced to British factories. German tanks tended to be more complex and sophisticated than their Allied counterparts, with features that enhanced battlefield performance but made mass production difficult. German factories continued to use relatively craft-intensive production methods, achieving high quality but limited quantity. This represented a strategic choice to prioritize individual vehicle capability over numerical superiority, a choice that made sense given Germany's industrial limitations, but that ultimately proved inadequate against the massive production capabilities of the United States and Soviet Union. The American experience provides another revealing comparison. When American industry began producing tanks in large numbers after Pearl Harbor, it brought to the task the full arsenal of mass production techniques developed in the automotive industry. American factories achieved production rates that dwarfed anything Britain or Germany could manage, turning out thousands of tanks per month from vast purpose-built facilities. Yet American success was not simply a matter of scale. It reflected the same fundamental principles that WWII had introduced to British industry: precision, standardization, flow production, systematic quality control. The difference was that American industry already understood these principles from decades of automotive production, while British industry had to learn them under the pressure of wartime urgency. The Soviet Union's approach was different again, emphasizing extreme simplification of design to achieve maximum production with limited manufacturing capability. Soviet tanks like the T-34 were remarkably effective despite their simplicity, or perhaps because of it, combining adequate battlefield performance with production methods that could be implemented in hastily built factories with inexperienced workers. Soviet industry achieved production numbers comparable to American industry, despite having far less sophisticated manufacturing infrastructure, demonstrating yet another approach to the challenge of mass producing complex military equipment under wartime conditions. These different national approaches to tank production reflected not just different industrial capabilities but different strategic philosophies and economic systems. Britain's transformation under WWII's influence represented a middle path between German sophistication and Soviet simplification, achieving a balance of quality and quantity that suited Britain's strategic situation and industrial capacity. The success of this approach validated the fundamental insight that modern manufacturing methods could be applied to military production, regardless of specific design choices or national industrial characteristics. The technical details of WWII's redesigns reveal the depth of his understanding of manufacturing principles. Consider the seemingly simple problem of bolt holes in armor plate. Traditional practice was to mark hole positions manually, then drill them using handheld or pedestal drills. This method was flexible but imprecise, with hole positions varying by several millimeters, depending on operator care and skill. WWII introduced precision drilling jigs, fixtures that held plates in exact positions while guiding drill bits to predetermined locations. These jigs were expensive to design and manufacture, but they ensured that every plate had holes in exactly the same positions, allowing plates to be truly interchangeable. Similarly, welding of hull components traditionally relied heavily on welder skill, with experienced welders adjusting their technique to account for variations in fit-up and material condition. WWII redesigned weld joints to minimize the skill required, using precisely machined edges that fit together consistently, specified filler materials and welding parameters, and inspection criteria that could be applied objectively. The result was not only faster welding, but more consistent weld quality, reducing the risk of cracks or failures that could compromise vehicle integrity. The transformation of supply chains was equally fundamental. Traditional craft manufacturing could tolerate substantial variation in component supply, as skilled workers would adapt to whatever materials and components were available. Flow production required far tighter coordination, with components arriving not just in the right quantities, but at the right times, meeting precise specifications that allowed immediate use without inspection or rework. This demanded new relationships with suppliers, with detailed specifications, quality requirements, and delivery schedules that many suppliers initially struggled to meet. WWII worked closely with supplier companies to help them implement the same kind of manufacturing improvements that were transforming tank factories, creating a cascade of improvement throughout the industrial supply chain. The training programs developed to support this transformation were themselves innovations, creating new approaches to industrial education that influenced manufacturing training for decades afterward. Traditional apprenticeship had been largely informal, with learning happening through observation and practice under experienced workers. The new system required formal training programs with structured curricula, practice exercises, and objective assessment of competence. These programs had to teach not just specific operations but underlying principles, giving workers enough understanding to recognize and solve problems, rather than simply following rote procedures. The measurement and metrics, systems introduced alongside flow production, represented another fundamental change. Traditional craft manufacturing was difficult to measure precisely. Production was tracked by counting completed units, but there was little visibility into what happened during production, why some tanks took longer than others, where delays and problems occurred. Flow production enabled and required detailed measurement at every stage. Cycle times for each operation, defect rates for each component, utilization rates for each machine, productivity metrics for each workstation. This data allowed systematic identification of bottlenecks and problems, enabling continuous improvement that gradually raised productivity and quality. The role of engineering drawings and specifications evolved significantly during this transformation. Traditional practice treated drawings as guides rather than absolute specifications, with the understanding that skilled workers would interpret them intelligently, adapting to practical realities of materials and manufacturing. WWII insisted on treating drawings as precise specifications that defined exactly what was to be produced, with tolerances that reflected functional requirements and manufacturing capabilities. This required far more careful engineering, with designers thinking through every detail of how components would be manufactured and assembled, but it enabled the kind of precision and consistency that flow production required. The cultural transformation within factories was perhaps as significant as the technical transformation. Workers accustomed to craft manufacturing had to learn to value consistency over adaptation, precision over judgment, systematic procedure over skilled improvisation. This was not simply a matter of learning new skills, but of adopting new attitudes toward work and quality. The transition was not always smooth, with some experienced workers resenting what they saw as de-skilling of their craft, while younger workers often adapted more readily to the new methods. Successful implementation required careful attention to human factors, explaining the reasons for changes, involving workers in problem solving, recognizing and rewarding competence in the new methods. Management culture also had to change. Traditional management of craft production had been relatively hands-off, with managers setting overall priorities, but leaving detailed execution to skilled workers. Flow production required far more active management with systematic planning, real-time monitoring, rapid problem-solving, and continuous attention to maintaining smooth flow. This demanded different skills and temperaments in managers, favoring systematic analytical thinking over the personal relationships and craft knowledge that had characterized traditional management. The transformation ultimately succeeded because it was not merely imposed from above, but became a collaborative effort involving workers, supervisors, managers, and engineers at all levels. Weeks provided the vision and technical framework, but countless individuals contributed to working out the details, solving unexpected problems, adapting general principles to specific circumstances. This distributed innovation was crucial to success, as no single person could have anticipated or solved all the challenges that emerged during implementation. The legacy of this transformation extends far beyond World War II tank production. The principles established during this period became foundational to modern manufacturing across virtually all industries. Today's automotive plants, electronics factories, pharmaceutical production facilities, and countless other manufacturing operations all employ descendants of the methods that Weeks introduced to British tank factories in the early 1940s. The continuous improvement philosophy that characterizes modern manufacturing, the emphasis on quality built into processes rather than inspected into products, the systematic use of data to identify and solve problems. All these can be traced back to the wartime transformation of armaments. Production. The story also reminds us that effective innovation requires not just good ideas, but sustained effort to implement them in the face of inevitable difficulties and resistance. Weeks's initial concept was relatively straightforward: apply automotive manufacturing principles to tank production. But the execution required years of detailed work, overcoming hundreds of specific challenges, convincing skeptics through demonstrated results rather than theoretical arguments. This persistence in the face of obstacles, this willingness to work through tedious details to achieve a larger vision, is characteristic of successful innovation in any field. Looking back across the decades, we can see how this episode illuminates broader themes in technological and social change. The tension between craft tradition and mass production that played out in British tank factories reflects a tension that has appeared throughout industrial history, as new methods challenge established practices and threaten existing skills and social arrangements. The resolution is never simple or complete. Modern manufacturing retains elements of craft skill, even as it embraces systematic method, and successful operations blend human judgment with technical precision. But the direction of change is clear: toward greater standardization, more precise control, more systematic organization of work. We can also see how wartime urgency accelerated changes that would likely have occurred eventually but far more slowly in peacetime. The British armaments industry of 1939 would probably have gradually adopted automotive manufacturing methods over subsequent decades as competitive pressure and technological change made traditional methods increasingly obsolete. War compressed this evolution into a few intense years, forcing rapid adaptation that would have been far more difficult to achieve in normal circumstances. This acceleration came at enormous cost in human terms, but it produced lasting benefits that shaped the post-war world. The human dimension of this story deserves emphasis. Behind the technical transformations and production statistics were hundreds of thousands of individuals whose lives were affected. Workers learning new skills, managers adapting to new methods, engineers solving unprecedented problems, families depending on wages from factory jobs, soldiers whose survival depended on having adequate equipment. Weeks himself was just one person, but his work touched all these lives, contributing in countless indirect ways to the final outcome of the war and the shape of the post-war world. This reminds us that history is made not just by famous leaders and dramatic battles, but by the accumulated efforts of many people working on seemingly mundane problems whose solutions prove to have far-reaching consequences. As we conclude this examination of how one designer's blueprint transformed tank production, we might reflect on what it tells us about human creativity and adaptation. The story is not one of genius invention or revolutionary breakthrough, but rather of intelligent adaptation, careful analysis, systematic problem-solving, and persistent implementation. These qualities, less dramatic than heroic brilliance but perhaps more important in practice, enabled Weeks and those who worked with him to achieve something truly remarkable: the transformation of an entire industry under the most demanding circumstances imaginable. contributing materially to victory in a conflict that determined the fate of nations and the course of the 20th century. The tanks that rolled off British assembly lines in the later years of the war were not just products of steel and machinery. They were embodiments of human ingenuity, persistence, and the power of systematic thought applied to practical problems. In that sense, they represented something fundamentally hopeful: the capacity of human beings to solve difficult problems through intelligence, collaboration, and determined effort, even in the darkest of times. Collaboration and determined effort, even in the darkest of times.